Hello everyone. Today I would like to talk about the paper related to the recommender system. It's quite an interesting topic, and the topic is called Metric Factorization Technique for Recommender System. It's published in 2009. And here is the table content. We will start with the abstract, followed by the recommender systems strategies, metric factorization method, learning algorithms, adding bias, additional input sources, temporal dynamics, input with varying confidence levels, Netflix price competition, current Netflix recommender system, and conclusion. Here is the abstract. Metric factorization models, as shown in the Netflix price competitions, are better than traditional nearest neighbor methods for making recommendations. They can include more detail like implicit feedback, time-related effects, and confidence levels. They can also efficiently handle large sparse metrics, which is common in recommendation systems where users typically interact with only a small fraction of available items. Before we get into the metric factorization, let's look at the two common approaches in recommendation systems. The first one is content filtering. This method recommends items based on the feature of the items and the profile of the user preference. It works by matching the feature of the items, for example, genre artist, tempo for music, with the user preference, for example, favorite genre, artist. Profile will enable program to connect user with product that align with their preference. Content-based filtering is based on the idea that if a user likes certain items in the past, they are likely to enjoy similar items in the future. It does not require knowledge or input from other users. In collaborative filtering, this method recommends items based on the preference of other users. It identifies users who have similar preference to the target user and recommend items that they have liked in the past, but the target user had not yet interacted with. Collaborative filtering is versatile across domains and can handle complex data better than content filtering. Is often more accurate but faces a challenge with new product user known as the cold start problem, which means it had difficulties recommending items for new user or items that have not yet received enough rating. In this sense, the content filtering excel. There are two major areas in collaborative filtering. The first one is neighborhood methods, which is divided into two categories. The first category is item-oriented approach. The system recommends items to a user based on the rating or preference of that user for similar items. For example, if a user has rated action movie highly, the system might recommend other action movies to that user. And the second category is user-oriented approach. The system finds users whose tastes are similar to the target user and suggests items that this similar user have enjoyed but the target user had not yet tried. We can look at the figure below for the user-oriented approach. Here we can see that Joe liked three movies on the left-hand side, And to make a prediction for him, the system will find the similar user who also like those movies, which is T people in the middle here as an example. They also like those three movies. And then in this case, all three also like the movie called Saving Private Ryan. So that movie is going to be the first recommendation to Joe. Also, two of them like the movie called Dune, and that movie is going to be the next that is recommended to Joe. Right. The second area is latent factor models. It represents both user and items in a lower dimensional space called latent space based on their ratings. These models aim to uncover hidden latent factors that explain the observed ratings. These factors can represent different aspects of items like comedies or drama for movies. And for user, each factor measures how much the user like movies that score high on the corresponding movie factors. Let's consider the simplified example with two dimensions. One represents female-oriented versus male-oriented, and the others serious versus escapist movies. In this example, movies and user are placed on these dimensions. For this model, a user predicted rating for a movie relative to the movie average rating is calculated as the dot products of the movie and user position on the graph. For instance, we would expect Gus to love Dumb and Dumber and hate the color purple and red Braveheart above average based on their position on the graph. Some of the most successful realizations of latent factor models are based on metric factorization. Recommender systems rely on structured data arranged in a metric format with user along one dimension and item of interest along the other. The most valuable data is explicit feedback, such as star ratings for movie on Netflix or thumbs up, down interactions on TiVo. However, this explicit feedback is often sparse, as users typically rate only a fraction of available items. Metric factorization offers the advantage of incorporating additional information beyond explicit rating. In cases where explicit feedback is lacking, recommender system can utilize implicit feedback derived from user behavior. This implicit feedback, which include actions like purchase history, browsing pattern, and search query, provides valuable insights into user preference. Unlike explicit feedback, implicit feedback results in a denser metric representation due to the greater volume of data generated by user interaction. In its basic form, metric factorizations represent both user and item in a shared latent factor space. This space has a dimensionality denoted by F. In this space, user-item interactions are represented as inner product, where each item I is associated with a vector Qi, and each user U is associated with a vector Pu, and the R hat UI is the rate for that user with that specific item. Here is a simplified example to represent the equation discussed previously. Let's assume that we have three users ABC that like or doesn't like comedy and action. If that user like it, the value is equal to 1. If the user doesn't like it, the value is equal to 0. And then we have each movie in the system that is associated with a score that indicate how much it represents comedy and actions. To predict the rating for a specific user and movie, we can simply multiply the corresponding user role by the movie column in the factorized metric, and then we will get the predicted rating for that user and that movie. Metric factorization models are similar to singular value decomposition, a technique for identifying latent factors in information retrieval. Applying SVD to collaborative filterings can be challenging due to the high number of missing values in the user item rating metric. Imputation to fill in missing rating can be expensive and inaccurate. More recent work suggests modeling only the observed rating to avoid overfitting, minimizing the regularized square error on the no rating to learn factor vectors. And here's the below is the equation that we need to minimize. Here is the learning algorithms. To approach to minimizing the equation in the previous slide are stochastic gradient descents and alternating least squares. The first one, SGD stochastic gradient descent, is an iterative optimization algorithm used to minimize an objective function. In the context of metric factorization, the objective function is typically the sum of the square error between the predicted rating and the actual ratings. The algorithm works by iteratively updating the factor vectors for user and items based on the gradient of the objective function with respect to these vectors. And the update rule for SGD in metric factorization can be represented as follows with these two equations. Here, PU and QI are the user and item factor vectors. EUI is the error between the predicted and actual ratings for user U and item I. Alpha here is the learning rate, and lambda is the regularization parameters. The second approach is alternating least squares, or ALS. ALS is another iterative optimization algorithm used for metric factorization. It alternates between updating the user factors and fixing the item factors, and vice versa. In each iteration, ALS solves a least square problem to update one set of factors while keeping the other set fixed. The update rule for ALS can be represented as follows with these two equations. Here P and Q are metrics containing the user and item factors. RU and RI are the user item rating metrics, and lambda is the regularization parameters. Both SGDs and ALS are used to learn the factor vectors in metric factorization model, with ALS being more popular due to its efficiency and ability to handle missing data.
The matrix factorization approach to collaborative filtering is flexible enough to deal with various data aspects and other application-specific variables. It is important to update the prior equations while staying within the same learning algorithm framework. Biases are added to account for the observed variation within the observations. For example, collaborative filtering usually has large systematic tendencies for items to have higher or lower ratings than other items, because a good product should be perceived as better than a bad product. Because biases capture much of the observed signal, it's necessary to model them accurately. The equation shown is the first order bias estimate. From left to right, the parameters of the equation are the global average, which is the average rating across all users for all items, the item bias, which is how different this item is compared to other items, and the user bias, which is how different the given user rates items compared to the average user. For example, suppose that you want a first order estimate for a user Joe, his rating of the movie Titanic. Now, say that the average rating over all movies in this system, which is the global average, is 3.7 stars. But Titanic is better than an average movie, so it tends to be rated about half a star above the average. This is the item bias. On the other hand, Joe is a critical user who tends to rate 0.3 stars lower than average. This is the user bias. Thus, the estimate for Titanic's rating by the user Joe would be 3.9 stars, which is 3.7 plus 0.5 minus 0.3. Here, we extend the user rating equation to include the bias equation from the previous slide. So now the user-item interaction is present within the bias in the same equation. This equation allows each component to explain the part of the signal relevant to it. The system learns this by minimizing the squared error function shown here. Any recommendation system will have to deal with the cold start problem. This problem occurs when a given user does not provide enough explicit feedback, so the model has a hard time reaching conclusions on the user's preference. In the example of Netflix, the cold start problem occurs when a user watches several shows or movies, but almost never gives a rating. One potential solution to the cold start problem is through the use of implicit feedback, which indirectly reflects opinion by observing user behavior such as purchase history, browsing history, search patterns, or even mouse movements. Implicit feedback usually denotes the presence or absence of an event, so it is typically represented by a densely filled matrix. Another often used information source is known as user attributes. This is usually related to the demographics of the user. This can describe the age group, gender, the zip code the user resides in, or even their income level. The equation shown here is the updated model to integrate all signal sources up to this point, with enhances to user representation. The new items added are n, which takes the user u as a parameter. It denotes the set of items that the user has expressed an implicit preference for. The sum of x, where I is an element of the aforementioned set of items. This is the vector for a user who has shown preference for certain items and is normalized for scalability and interpretability. Lastly, the function a with parameter u for the user again is a set of attributes, and we create a distinct factor vector corresponding to each attribute to describe the user through that set of attributes. So far, all of the models presented have been static. In reality, all of the previous factors can evolve over time. Customers' taste can be completely different than it was 5 years prior. The system needs to account for the temporal effects and the dynamic, time-drifting nature of user-item interactions. The matrix factorization approach is easily adaptable to include temporal effects, which will significantly improve accuracy. Decomposing ratings into distinct terms allow the system to treat different temporal factors separately. Item bias, user bias, and user preferences will all ebb and flow with time. Item bias can change with time due to external events such as an actor's popularity or the effects used within the movie becoming too dated for a new user to enjoy. A user might become more critical of movies as they age, so they might rate an average movie at 3 stars instead of 4 stars like they would when they were less critical. A user's preference might change as the popularity of certain genres change with time as well, For example, if their favorite actor becomes the frontman of a new series in a genre the user has not explored before. Because of this, the user-item interaction should also be treated as a temporal effect. There are a multitude of reasons why the system needs to treat all of these factors as a function of time. It is worth noting that the item characteristics vector, Q, remains static, because unlike humans, items are static in nature. The equation shown replaces the now temporal factors with functions of time, t, for each factor.
In recommendation systems, not all observed ratings carry the same weight or confidence level. Factors like advertising influence and adversarial user behavior can skew ratings. Systems relying on implicit feedback face challenges in quantifying precise user preferences, often resorting to binary representations. To address this, attaching confidence scores to estimated preferences becomes valuable. The matrix factorization model can accommodate varying confidence levels, refining its cost function to give less weight to less meaningful observations. This enhancement improves the accuracy of recommendations. The equation below demonstrates how the model accounts for confidence levels in the optimization process. The confidence in observing the user's rating is denoted by the variable CUI, and the user's rating itself is denoted by RUI. This equation is the final version of our matrix factorization model. Real-life applications, such as collaborative filtering for implicit feedback datasets, further highlight the importance of considering varying confidence levels in recommendation systems. In 2006, Netflix launched a groundbreaking competition aimed at enhancing its recommendation system. This contest, the largest collaborative filtering event of its time, attracted a staggering 48,000 teams from 182 countries. Netflix provided a vast training set comprising over 100 million ratings from 500,000 customers on 7,000 movies. Teams were tasked with predicting ratings on a test set of 3 million ratings, with Netflix evaluating their performance based on root mean square error. The grand prize of $1 million awaited the team that could improve RMSE by 10% or more, with a consolation prize of $50,000 for the top scoring team if the goal wasn't achieved. This initiative sparked immense excitement in the collaborative filtering field, marking a significant leap forward in data availability for research and innovation. In summary, the Belcore team, comprising of Yehuda Koren, Robert Bell, and Chris Volinsky, made significant strides in the Netflix prize competition. They secured the 2007 Progress Prize with an 8.43% improvement over Netflix's performance, and later collaborated with Big Chaos to win the 2008 Progress Prize with a remarkable 9.46% lead. Their winning entries, which consisted of over 100 predictor sets, predominantly utilized matrix factorization models with various innovative methods. Their success underscored the effectiveness of complex factor models with detailed parameter sets, as well as the importance of incorporating temporal components to enhance accuracy. The Belcore team's achievements continue to influence the landscape of recommendation systems, emphasizing the power of collaboration and innovation in driving progress and excellence. After nearly 3 years of intense collaboration, Belcore won the $1 million Netflix prize for improving the company's movie recommendation algorithm by 10%. Belcore's Pragmatic Chaos, a hybrid team consisting of AT&T's Corebell and the Austrian team Big Chaos, clinched victory by submitting their solution just 10 minutes before the second place team. Despite both teams tying in terms of score, Belcore's Pragmatic Chaos secured the win due to their earlier submission. The contest, which began with over 50,000 contestants, saw the final showdown between these two teams, highlighting the significance of diverse approaches. While there were complaints about technique transparency, the winning team's strategy ultimately proved effective in achieving the desired improvement in the recommendation algorithm. Factorizing the Netflix user movie matrix unveils essential dimensions for predicting movie preferences, with Figure 3 showcasing the first two factors. The plot illustrates distinct genres, positioning movies based on their factor vectors. Notably, the axes delineated between Factor Vector 1, which displays lowbrow comedies and serious dramas with female leads, and Factor 2, which contrasts between independent quirky films and mainstream formulaic ones. Despite stylistic differences, movies like Annie Hall and Citizen Kane may neighbor each other due to shared classic status. This demonstrates how matrix factorization reveals latent factors that transcend traditional genre boundaries, offering nuanced insights into viewer preferences and film categorization. Figure 4 presents the impact of different implementations and parameterizations on matrix factorization models' accuracy, measured by RMSE, or root mean square error. It illustrates how variations in model complexity and dimensionality affect performance, with more refined models yielding lower RMSE scores. Notably, incorporating temporal components proves crucial due to significant temporal effects in the data. Ultimately, this analysis highlights the importance of fine-tuning factor models to achieve optimal accuracy in predicting user preferences. The Netflix prize competition took place when Netflix was still a DVD rental company. As Netflix shifted from DVD rental to streaming services, it faced the challenge of adapting its recommendation system to a new format. To address this, Netflix turned to advanced machine learning techniques, including matrix factorization, deep learning, and reinforcement learning. Matrix factorization helped Netflix analyze user preferences and viewing habits by decomposing the user-movie interaction matrix, as we have seen earlier in this presentation. Deep learning enabled the system to understand complex patterns in user behavior and make highly personalized recommendations. Additionally, reinforcement learning allowed Netflix to optimize its recommendation algorithms by experimenting with different approaches and measuring their impact on user engagement. Despite encountering challenges such as biases in data and the cold start problem for new users, Netflix continues to rely on machine learning to enhance its recommendation system. By leveraging these techniques, Netflix ensures that users receive personalized and diverse content suggestions tailored to their preferences, ultimately improving user satisfaction and retention. In conclusion, matrix factorization techniques have risen to prominence as the leading approach in collaborative filtering recommenders, outperforming classical methods in terms of accuracy. Their superiority stems from their capacity to integrate various factors such as implicit feedback, temporal dynamics, and confidence levels, leading to the development of more precise and resource-efficient models. The success of matrix factorization techniques, as evidenced by experiences with datasets like the Netflix prize data, highlights their effectiveness in capturing essential aspects of the data to enhance recommendation accuracy. By leveraging these techniques, recommendation systems can better understand user preferences and deliver tailored content suggestions, ultimately improving the user experience and engagement. The Works Cited section provides a list of references used to gather information and support the content shown in this presentation. These works include research papers, articles, and other relevant materials that have informed our understanding of the topics discussed. As we come to the end of this presentation, we'd like to extend our gratitude to each of you for your attention and engagement. We'd like to also express our appreciation to the authors and researchers whose work has served as the foundation for this presentation. Thank you for listening.